In mathematics, an integral assigns numbers to functions in a way that can describe displacement, area, volume, and other concepts that arise by combining infinitesimal data. Integration is one of the two main operations in calculus, with its inverse, differentiation, being the other. Given a function f of a real variable x and an interval a, b of the real line, the definite integral is defined informally as the signed area of the region in the xy plane that is bounded by the graph of f. The x-axis and the vertical lines x equals a and x equals b. The area above the x-axis adds to the total and that below the x-axis subtracts from the total. Roughly speaking, the operation of integration is the reverse of differentiation. In this case, it is called an indefinite integral and is written. The integrals discussed in this article are those termed definite integrals. It is the fundamental theorem of calculus that connects differentiation with the definite integral. If f is a continuous real-valued function defined on a closed interval a, b, then, once an antiderivative f of f is known, the definite integral of f over that interval as given by the principles of integration were formulated independently by Isaac Newton and Gottfried Leibniz in the late 17th century. Who thought of the integral as an infinite sum of rectangles of infinitesimal width. A rigorous mathematical definition of the integral was given by Bernhard Riemann. It is based on a limiting procedure which approximates the area of a curvilinear region by breaking the region into thin vertical slabs. Beginning in the 19th century, more sophisticated notions of integrals began to appear, where the type of the function as well as the domain over which the integration is performed has been generalized. A line integral is defined for functions of 2 or 3 variables, and the interval of integration, a, b, is replaced by a certain curve connecting 2 points on the plane or in the space. In a surface integral, the curve is replaced by a piece of a surface in the three-dimensional space. History. Precalculus integration. The first documented systematic technique capable of determining integrals is the method of exhaustion of the ancient Greek astronomer Eudoxus, which sought to find areas and volumes by breaking them up into an infinite number of divisions for which the area or volume was known. This method was further developed and employed by Archimedes in the 3rd century BC and used to calculate areas for parabolas and an approximation to the area of a circle. A similar method was independently developed in China around the 3rd century AD by Liu Hui, who used it to find the area of the circle. This method was later used in the 5th century by Chinese father and son mathematicians Zhu Chongji and Zhu Geng to find the volume of a sphere. The next significant advances in integral calculus did not begin to appear until the 16th century. At this time the work of Cavalieri with his method of indivisibles, and work by Fermat began to lay the foundations of modern calculus. With Cavalieri computing the integrals of xn up to degree n equals 9 in Cavalieri's quadrature formula. Further steps were made in the early 17th century by Barrow and Torricelli, who provided the first hints of a connection between integration and differentiation. Barrow provided the first proof of the fundamental theorem of calculus. Wallace generalized Cavalieri's method, computing integrals of x to a general power, including negative powers and fractional powers. Newton and Leibniz. The major advance in integration came in the 17th century with the independent discovery of the fundamental theorem of calculus by Newton and Leibniz. The theorem demonstrates a connection between integration and differentiation. This connection, combined with the comparative ease of differentiation, can be exploited to calculate integrals. In particular, the fundamental theorem of calculus allows one to solve a much broader class of problems. Equal in importance is the comprehensive mathematical framework that both Newton and Leibniz developed. Given the name infinitesimal calculus, it allowed for precise analysis of functions within continuous domains. This framework eventually became modern calculus, whose notation for integrals is drawn directly from the work of Leibniz. formalization. While Newton and Leibniz provided a systematic approach to integration, their work lacked a degree of rigor. Bishop Berkeley memorably attacked the vanishing increments used by Newton, calling them ghosts of departed quantities. Calculus acquired a firmer footing with the development of limits. Integration was first rigorously formalized using limits by Riemann. Although all bounded piecewise continuous functions are Riemann integrable on a bounded interval, subsequently more general functions were considered, particularly in the context of Fourier analysis, to which Riemann's definition does not apply, and Lebesgue formulated a different definition of integral, founded in measure theory. Other definitions of integral, extending Riemann's and Lebesgue's approaches, were proposed. These approaches based on the real number system are the ones most common today, but alternative approaches exist, such as a definition of integral as the standard part of an infinite Riemann sum, based on the hyperreal number system. Historical notation. Isaac Newton used a small vertical bar above a variable to indicate integration, or place the variable inside a box. The vertical bar was easily confused with x or x, which Newton used to indicate differentiation, and the box notation was difficult for printers to reproduce, so these notations were not widely adopted. The modern notation for the indefinite integral was introduced by Gottfried Leibniz in 1675. He adapted the integral symbol from the letter standing for summa. The modern notation for the definite integral, with limits above and below the integral sign, was first used by Joseph Fourier in Memoirs of the French Academy around 1819-20, reprinted in his book of 1822. Terminology and notation. Standard. The integral with respect to x of a real-valued function f of a real variable x on the interval a, b, is written as the integral sign represents integration. The symbol dx, called the differential of the variable x, indicates that the variable of integration is x. The function f to be integrated is called the integrand. The symbol dx is separated from the integrand by a space. If a function has an integral, it is said to be integrable. The points a and b are called the limits of the integral. An integral where the limits are specified is called the definite integral. The integral is said to be over the interval a, b. When the limits are omitted, as in the integral, is called an indefinite integral. The fundamental theorem of calculus relates indefinite integrals and definite integrals. There are many extensions of this notation to generalizations of the integral. Variants in modern Arabic mathematical notation. A reflected integral symbol is used instead of the symbol. Some authors use an upright d to indicate the variable of integration. The symbol dx is not always placed after f, as for instance in interpretations of the integral. Integrals appear in many practical situations. If a swimming pool is rectangular with a flat bottom, then from its length, width, and depth we can easily determine the volume of water it can contain, the area of its surface, and the length of its edge. But if it is oval with a rounded bottom, all of these quantities call for integrals. Practical approximations may suffice for such trivial examples, but precision engineering requires exact and rigorous values for these elements. To start off, consider the curve y equals f between x equals 0 and x equals 1 with f equals square root x. We ask, what is the area under the function f, in the interval from 0 to 1, and call this area the integral of f. The notation for this integral will be as a first approximation. Look at the unit square given by the sides x equals 0 to x equals 1 and y equals f equals 0 and y equals f equals 1. Its area is exactly 1. As it is, the true value of the integral must be somewhat less than 1. Decreasing the width of the approximation rectangles and increasing the number of rectangles shall give a better result, so cross the interval in 5 steps. Using the approximation points 0, 1/5, 2/5, and so on to 1. Fit a box for each step using the right end height of each curve piece, thus square root 1/5, square root 2/5, and so on to square root 1 equals 1. Summing the areas of these rectangles, we get a better approximation for the sought integral. Namely, we are taking a sum of finitely many function values of f, multiplied with the differences of two subsequent approximation points. We can easily see that the approximation is still too large. Using more steps produces a closer approximation, but will never be exact. Replacing the 5 subintervals by 12 in the same way, but with the left-end height of each piece, we will get an approximate value for the area of 0.6203, which is too small. The key idea is the transition from adding finitely many differences of approximation points multiplied by their respective function values to using infinitely many fine, or infinitesimal steps. The notation conceives the integral as a weighted sum, denoted by the elongated s, of function values, f, multiplied by infinitesimal step widths, the so-called differentials, denoted by dx. The multiplication sign is usually omitted. Historically, after the failure of early efforts to rigorously interpret infinitesimals, Riemann formally defined integrals as a limit of weighted sums, so that the dx suggested the limit of a difference. Shortcomings of Riemann's dependence on intervals and continuity motivated newer definitions, especially the Lebesgue integral, which is founded on an ability to extend the idea of measure in much more flexible ways. Thus the notation refers to a weighted sum in which the function values are partitioned, with mu measuring the weight to be assigned to each value. Here A denotes the region of integration. Formal definitions. There are many ways of formally defining an integral, not all of which are equivalent. The differences exist mostly to deal with differing special cases which may not be integrable under other definitions, but also occasionally for pedagogical reasons. The most commonly used definitions of integral are Riemann integrals and Lebesgue integrals. Riemann integral. The Riemann integral is defined in terms of Riemann sums of functions with respect to tagged partitions of an interval. Let a, b be a closed interval of the real line, then a tagged partition of a, b is a finite sequence. This partitions the interval a, b into n subintervals xi-1, xi, indexed by I, each of which is tagged with a distinguished point t, xi-1, xi. A Riemann sum of a function f with respect to such a tagged partition is defined as thus: each term of the sum is the area of a rectangle with height equal to the function value at the distinguished point of the given subinterval, and width the same as the subinterval width. Let delta I equals xi-1 be the width of subinterval I, then the mesh of such a tagged partition is the width of the largest subinterval formed by the partition. Max E equals 1, n delta I. The Riemann integral of a function f over the interval a, b is equal to s if, for all epsilon greater than 0, there exists delta greater than 0, such that, for any tagged partition a, b with mesh less than delta, we have when the chosen tags give the maximum value of each interval, the Riemann sum becomes an upper Darboux sum, suggesting the close connection between the Riemann integral and the Darboux integral. Lebesgue integral. It is often of interest, both in theory and applications, to be able to pass to the limit under the integral. For instance, a sequence of functions can frequently be constructed that approximate, in a suitable sense, the solution to a problem. Then the integral of the solution function should be the limit of the integrals of the approximations. However, many functions that can be obtained as limits are not Riemann integrable, and so such limit theorems do not hold with the Riemann integral. Therefore, it is of great importance to have a definition of the integral that allows a wider class of functions to be integrated. Such an integral is the Lebesgue integral, that exploits the following fact to enlarge the class of integrable functions. If the values of a function are rearranged over the domain, the integral of a function should remain the same. Thus Henri Lebesgue introduced the integral bearing his name, explaining this integral thus in a letter to Paul Montel: I have to pay a certain sum, which I have collected in my pocket. I take the bills and coins out of my pocket and give them to the creditor in the order I find them until I have reached the total sum. This is the Riemann integral. But I can proceed differently. After I have taken all the money out of my pocket, I order the bills and coins according to identical values, and then I pay the several heaps one after the other to the creditor. This is my integral. Siegmund Schultz as follows puts it: to compute the Riemann integral of f, one partitions the domain a, b into subintervals, while in the Lebesgue integral, one is in effect partitioning the range of f. The definition of the Lebesgue integral thus begins with a measure. In the simplest case, the Lebesgue measure mu of an interval a equals a, b is its width, b minus a, so that the Lebesgue integral agrees with the Riemann integral when both exist. In more complicated cases, the sets being measured can be highly fragmented, with no continuity and no resemblance to intervals. Using the partitioning the range of f philosophy, the integral of a non-negative function f, our R should be the sum over T of the areas between a thin horizontal strip between y equals T and y equals T plus dt. This area is just mu x, f greater than T, dt. Let f equals mu x, f greater than T. The Lebesgue integral of f is then defined by where the integral on the right is an ordinary improper Riemann integral. For a suitable class of functions, this defines the Lebesgue integral. A general measurable function f is Lebesgue integrable if the area between the graph of f and the x-axis is finite. In that case, the integral is, as in the Riemannian case, the difference between the area above the x-axis and the area below the x-axis. Where other integrals, although the Riemann and Lebesgue integrals are the most widely used definitions of the integral, a number of others exist, including the Darboux integral, which is constructed using Darboux sums and is equivalent to a Riemann integral, meaning that a function is Darboux integrable if and only if it is Riemann integrable. Darboux integrals have the advantage of being simpler to define than Riemann integrals. The Riemann-Stieltjes integral, an extension of the Riemann integral. The Lebesgue-Stieltjes integral, further developed by Johann Radon, which generalizes the Riemann-Stieltjes and Lebesgue integrals. The Daniell integral, which subsumes the Lebesgue integral and Lebesgue-Stieltjes integral without the dependence on measures. The Haar integral, used for integration on locally compact topological groups, introduced by Alfred Haar in 1933. The Henstock-Kurzweil integral, variously defined by Arnaud Denjoy, Oskar Perrin, and Jaroslav Kurzweil, and developed by Ralph Henstock. The Ito integral and Stratonovich integral, which define integration with respect to semi-martingales such as Brownian motion. The Young integral, which is a kind of Riemann-Stieltjes integral with respect to certain functions of unbounded variation. The rough path integral, which is defined for functions equipped with some additional rough path structure and generalizes stochastic integration against both semi-martingales and processes such as the fractional Brownian motion.